everyone! This is June. OpenAI just announced reinforcement fine-tuning on its day 2 of announcements. They unleashed GPT-01, their latest and greatest model iteration on day 1, and unveiled a groundbreaking new training technique, reinforcement fine-tuning on day 2, an upgrade to their supervised fine-tuning method. Let's dive deep into the details, separating fact from fiction and exploring both the incredible potential and the inherent challenges of this technology. First, a quick word on GPT-01. OpenAI released this improved model iteration on day 1. It's now powering ChatGPT and will soon have an API. They highlighted enhanced thinking time, suggesting improved contextual understanding. Please check out our full review of it on our channel. The link is given in the description. While a welcome improvement, this is essentially an incremental upgrade, not a paradigm shift. The real story here is reinforcement fine-tuning. Before diving deep into reinforcement learning, let's quickly talk about how supervised fine-tuning and reinforcement learning works on its own. First, let's talk about fine-tuning. We take a trained model like GPT-4o or GPT-01, and then we fine-tune it on a smaller, more specific dataset. This helps the model adapt to new tasks and improve its performance. For example, a company may fine-tune a model to answer questions about its products. Now, how does someone do it? Last year, OpenAI released the supervised fine-tuning. Essentially, we use a labeled dataset to fine-tune the model. It's like we provide a set of questions and their answers. Once the model is trained, it can map the question to the relevant answer. Maybe Jingyong can benefit from this? You know, create something more than just a hot dog or not hot dog app. Now, let's talk about reinforcement fine-tuning. But what is reinforcement learning in the first place, you might ask? Imagine training a dog. You don't just tell it what to do. You reward it when it behaves correctly and discourage it when it doesn't. Reinforcement learning works similarly. We define a reward function that tells the AI model how well it's performing. The model then learns to maximize this reward by adjusting its behavior. So, now you can think of what an amazing advancement OpenAI has made. Reinforcement fine-tuning, RFT, works by combining the best of both worlds, the efficiency of fine-tuning and the power of reinforcement learning. We start with a pre-trained model like GPT-01. You present the model with a problem, allow it to formulate a response, and then provide graded feedback. This feedback isn't a simple binary, correct or incorrect. It's a nuanced score reflecting the quality and accuracy of the response. The model then uses this graded feedback to adjust its internal reasoning processes. Correct lines of thinking are rewarded, incorrect ones are penalized, subtly shaping the model's future behavior. The efficiency is simply amazing. The demo showcased dramatic improvements with as few as a dozen training examples, a fraction of the data required for traditional fine-tuning. This efficiency dramatically reduces the barrier to entry for developing highly specialized AI models. Let's look at the example they showcased in their live stream. The real-world application they chose was incredibly compelling, diagnosing rare genetic diseases. This wasn't a theoretical exercise, it was a genuine collaboration with researchers at Berkeley Lab and Chairide Hospital. They used RFT to train the GPT-01 mini model to identify the gene that causes a rare disease based solely on a patient's symptom profile, including the critical inclusion of absent symptoms. They selected a suitable method, base model, GPT-01 Mini Alpha, and curated a relevant dataset in JSON format of patient symptom profiles and corresponding causative genes. They also had a validation dataset which is needed to check the model's performance at the end of training and then adjust the hyperparameters to get better performance. They mentioned there was no overlap between the genes present in both sets. Otherwise, the model would simply memorize the associations between symptoms and genes, and it would no longer be reinforcement learning. Instead, the model is forced to generalize from the training data and apply its learning to unseen data in the validation set. Where does reinforcement learning play a part? This is where graders come in. Graders are automated scoring systems. They compare the model's output to the correct answer in the training dataset and assign a score between 0 and 1. A score of 0 indicates a completely incorrect response, while a score of 1 signifies a perfectly correct answer. Partial credit can also be awarded for partially correct responses, allowing for a nuanced evaluation. For example, the model's output would be a list of answers it thinks are correct, with the first object in the list being the most probable answer, to the last one being the least probable answer. Now, if the model's output had the correct answer in the second position of the list, it would be given a grade of 0.7, for example, indicating that it is close to a correct answer, but not quite there. The platform offers a variety of pre-built graders designed to cover a wide range of potential tasks. These graders can effectively evaluate model performance and provide feedback, guiding the fine-tuning process. OpenAI is continuously expanding its collection of graders, and future updates may enable users to create custom graders tailored to their specific needs. It strikes a perfect balance between ease of use and the necessary flexibility for highly specialized applications. This modular design is what truly sets RFT apart. Here are the evaluation results they shared during the demonstration. The models seem to have about a 30% accuracy with the answer in the top position in the list, 41% accuracy with the answer being in the top 5 position, and 45% accuracy with the correct answer being in the list at all. Now these numbers may not look as impressive, but looking at the score of the original O1 mini model, there is almost 2 times the performance improvement. Something to note that Justin from the Berkeley lab also pointed out is it's not an apple-to-apples comparison to the existing bioinformatics tools since they didn't provide the genomic sequencing data. Currently, the model is outputting the list of correct genes with an incomplete list of symptoms, which is great. You can also better understand by looking at the provided graph, which illustrates the performance of different models on a gene identification task, measured by 3 metrics: top at 1, top at 5, and top at max. The O1 Mini fine-tuned model consistently outperforms both the original O1 Mini and the larger O1 model across all metrics. This also demonstrates the effectiveness of reinforcement fine-tuning in improving model performance on specific tasks. The graph highlights the significant boost in accuracy, particularly for the top at 1 metric, indicating that the fine-tuned model is more likely to identify the correct gene as the top prediction. The fact that GPT-O1 Mini, a smaller, less computationally intensive model, outperformed the larger GPT-O1 on this specific task is a resounding testament to RFT's power. RFT has the potential to accelerate AI development exponentially. Imagine hyper-personalized medicine, more accurate financial models, legal systems aided by insightful AI assistants, and scientific breakthroughs fueled by AI that truly understands complex data. However, we must actively address the ethical concerns surrounding bias, transparency, explainability, and the responsible use of such powerful technology. Let's discuss. What are your thoughts? What are the most promising applications, and what are the most pressing concerns? Let's keep the conversation going in the comments section below. And don't forget to like, share, and subscribe for more critical analysis of the ever-evolving world of AI.